So the purpose of this lecture is to show you how to calculate a small sample confidence interval. Again, we will have future lectures in which we show you how we know that we can do this. That is to say, how we know that our sample can be treated as being normally distributed. Let us start here. I'm going to first clear everything out so I can talk about it one step at a time. I'm going to have to take a square root when I do my standard error in the mean. So from my NumPy module, I'm going to import the square root. And I'll be needing to use pandas. I'll import pandas. I'm going to need to use stats, so I'll import scipy.stats. And actually, I'm not going to be doing pictures on this one, and so I don't need to import my my graphics. Okay, so let's get this stuff imported. I'm going to pull in some fake data I've generated from the lab of Bertram B. Bottlebutt, who has some data on Bigfoot. And so input this as Bigfoot data. And we look in Bigfoot, just the top of it. And what I want us to see, we have several different things. We've got the foot size, because our scientist, Dr. Bottlebutt, has measured the feet and has weighed the livers of a certain number of Sasquatch. He's also noted their sex as male and female. So what we're going to have to do, we're going to have to separate one sex from the other, because there might be some sexual dimorphism. But let's look here. We have, again, 50 data items, and when we separate these by sex, we're very likely to fall below the 30 sample threshold. So in this square, this cell, I'm going to separate out the males, and go BF_male will be Bigfoot, where I'm going to just pick out the one where the sex is equal to male. And let's look at some info on that. And in doing that, I see that I have 3 different columns, and each of these columns has 27 data items in it. So I have 27 foot sizes, 27 liver weights, and 27 sexes. But since I've separated these all out to be male, all of my sexes will be M. Yeah, okay. So now let us draw what I have here. I'm going to get some data. I'm setting this up, get my sample size. That'll be, since each row is a sample, the number of rows will give us the sample size. The degrees of freedom is the sample size minus 1, and the level of confidence I'm setting to be 95. That's my choice. 95 is a very common level of confidence for confidence intervals. Now from my data, I'm going to look, I'm only interested in estimating the foot size. I may give as an exercise on this getting the liver weight. So my X bar is the mean of the foot size. I'm denoting it X bar because it is from a sample. This is sample data. I'm going to calculate the sample standard deviation of the foot size. That's going to be S. The standard error of the mean, which I denote as standard error, is S divided by the square root of, and I have it in here. I'm going to type in sample size just to emphasize that this is the concept, right? We're dividing our standard deviation by the square root of the sample size. my T alpha over 2, I calculate using stats.t.ppf, and then I 0.5 plus confidence level divided by 2. That gives me the number to put here, and then my degrees of freedom as my second argument. And I calculate here my margin of error as my T alpha 2 times the standard error of the mean. I shift, I enter, and those calculations are done. And now I'm interested in seeing what actual numbers I have. Okay. My X bar is 40 point, a bunch of 8s. My standard deviation, my sample standard deviation is 4.08 with a lot of misplaced accuracy there. My T sub alpha over 2 with my 26 degrees of freedom is 2.02555, etc. My standard error is 0.786 junk, and if I take my 2.05 times the 7.8, I'll get the 1.67. Okay, now my confidence interval. My X bar is an estimate, right? Remember, my X bar is always wrong, so I have to give it some leeway. It might be too big, so I subtract off my margin of error. It might be too small, so I add my margin of error. And so that gives me my confidence interval, which is 39.7, 0.27 to 42.51, rounded off. Because after a certain point, those decimals just become annoying. Anyway, so this again, and you'll note how similar it is to the way we do it for a large sample, just the difference with the degrees of freedom and the calculation of the t.